So it took me a while to think about what to say, but I decided on domain Markov properties, which is in a way something I have been thinking for quite a while in my life, but now there is somehow, I wouldn't say exactly a framework, but at least several different ideas that can take place together. So essentially what I am interested, or what we are going to discuss, is mostly what does the rigidity of the Markov property and the freedom of the Markov property from a statistical physics point of view, meaning I want somehow fields, so I want to understand the Markov property of fields. So it's not the Markov property on a line, as one is usually imagining when it has time and when it's a Markov property, but when one has a space. Okay? So essentially, what we want to ask are two essential questions. What we want to answer, sorry, is maybe switch the right. Which probability laws satisfy the Markov property? So this is the first type of question we want to say. So it's in a way, what is the rigidity of Markov properties? And the second type of question we want to ask is, assuming that someone gives you a probability measure on fields, the probability loss on fields. So for me, a field will be a function of phi that goes from a metric space M into something. Let's simplify. I'm putting R here, but here could be whatever. And then if someone gives you one of these fields satisfying the Markov property, the question is which random subset A of M satisfy the Markov property. Okay, so when M is just R plus, let's say, so the positive numbers, we are used to work with homogeneous or non-homogeneous Markov process, and we will realize that the Markov property is not always well defined. It does not always mean just one thing. It tends to mean different things according to the natural context where it is living, and somehow one knows that stopping times are type of random sets or random times that satisfy the Markov property. Okay, but it could be a question on whether these are the only ones or there are more than this. Is there something else that we are missing? And we are going to try to answer this in two or three contexts. So first one is the metric graph context. So these are like the chapters. The second one is random planar map. So now not only they are going to be random fields, but they are going to be living into a random environment, into a random graph itself. Random planar map. And if we have some time, I will discuss the continuous setting, continuous domain. Okay. So, to simplify life, I will start like in a paper, in the sense that I will just give you two results that I will need, and I will use it throughout the talk, so it will be better to have them together at the beginning. So it will be just something like preliminaries. So I will start. So essentially, a good friend for us in this talk will be the Brownian motion. We will want to go and look at the Brownian motion, we will look at Brownian bridges, but you have to think of it always like as an example. I mean, we are taking Brownian motion, but I could take, for most I want to say, I could take any continuous time Markov process, so it could be in discrete space, that has cat-like trajectories, and that has an invariant measure, that it doesn't have to be a probability measure, just an invariant measure. So for example, for Brownian motion, the invariant measure would be Lebesgue. It's not a probability measure. Yes?
So should I imagine this as a local set? Or
yes, exactly. So the question is, can you characterize local sets?
Okay.
And this will be, like your metrograph will be planar, it's like only in 2D, you're not saying anything about...
So in this case, no, it will be in general.
Okay.
In this case, it's planar maps, so yes. And this one, not necessary, no.
Okay.
So if I'm not 100% sure that I managed to talk something about this story. That is somehow... so maybe I can tell you. So this is based in a current work that we did last month with Leandro, Irene, and Weibu. And this is based in a joint work with Pablo and Luis Fredes. So I hope I will write it with stuff. So as you see, I'm not citing many people. That means that I hope that this is very basic. So if it's not, basic is always about what? Fundamental, in the sense that I'm not requiring a lot of things built up on it. We just need to be comfortable with Brownian motion and Brownian bridges, mostly, and then we will define random planar maps, but I hope I can define them in a way that it is simplifies it. Okay, so we will need certain notation. So PTX, this will be the log of Brownian motion. And I will keep trying to use these notations because I want to always emphasize that the Brownian motion is just an example. Okay? Until time t. And P small t x, this is the density with respect to the vector. Okay, so there is an x here, it's because it started at x. I hope I don't have to write it down. And of course, we also have a Brownian bridge. So this is the law of a Brownian bridge of length t. And if I write p t1 xy, this is the density of the Brownian bridge. Maybe should I write? Okay, we'll write W for Brownian motion and B for bridge. So these are known quantities, but I'm essentially going to. The only thing that it will matter to us is that they are continuous in all of the parameters. And yes. Okay, so let us write the law, the joint law of Brownian motion at time t, Brownian motion at time t1. T1 is always smaller than. Okay. So there are two ways of getting this law, and this is where our game is going to come. So the first way will be by using the definition of a Brownian bridge. So the definition of a Brownian bridge is tell us first we can sample WT. So this will have a joint density with respect to Lebesgue. We first sample this one, it gives us PT started from x, let's say. So I never said where I'm starting from x. At a point y. So let's let me but I didn't put that one, so let me call this C and this in the W. Okay, so I don't get confused. So here I get okay, I already did. So I get PT of x C. Okay, and if this one is in C, then W of T1 is, I just have to do a Brownian bridge running from time T1 up to time T1, but of length T, running from X to C, of at dW. Yes. So this is one possibility. I first sample the last point, and then I use the property of the Brownian bridge. But there is a second way, which is using the Markov property. So I could first go until time W of T1, and then restart at W of T1 and getting time T. So this could be something like P T1 of X of, so I have to arrive to W, and then I have to start in W and arrive to C. Okay. Okay, so in general, is this always true? In general, for getting the Brownian motion, everything I use in a way it has to do with Markov property. You know, it's like the definition of bridges. So you need to define a Markov bridge, and you have probability. So this is not always true. This is almost everywhere because it's a densities. So because things are continuous, this is always true for Brownian motion. Because if I'm continuous, I'm almost everywhere equal. I'm everywhere equal. So I will not worry that much about these things, but there is always this thing behind when one is working with densities. One doesn't get equalities, one gets almost everywhere equalities, and there are some. Okay?
Actually, is this a way to define the Brownian bridge in a way that you say somehow the unique process that this composition becomes this?
Good question. Could be, yes. Yes. I mean.
No, I just like it's like kind of non-technical definitions of objects.
Yeah, it could be. I'm not 100% sure because I mean that is for sure defines one point, but it doesn't. I don't know if it gives you the joint. So you have to do the joint thing. And for this, I will get. So what we would want to get. Is, so this will be like I will call this the magic formula. So this is the one magic formula. So this is the first useful stuff we need. The second thing we need. So we would want to do something like, okay, to run a Brownian bridge. So I take the probability of a Brownian bridge, a probability measure, and I want to run it from x to y. So this is a probability measure on the space of continuous curves. I would want to say that this is the same as running from x to c to in time t, from running from x to c in time t1, but restricting to the time 0 t1. Yeah, so that, but this I mean like a probability measure. I just restrict, I just do the projection and just look at the first time t1. Then I want to say, okay, this is the probability measure of t minus t1, running from c to y. From time t1 up to t, it's like a product measure, and where c is running on level. I want this to be true, but this is not true. It's a little bit tricky. This is not true because I am missing my magic formula. So it will almost be true when I do this. So let me explain what I'm saying. So by this I mean, so P check will just be the anormalized probability measure. So it will be the density of a Brownian motion from running from x to y times the normal probability measure of a Brownian bridge running from x to y. Okay, and essentially it comes out of the formula. So as it said, like you can take from 0, so you can sample the Brownian motion at time 0, t1 and t, and then what you have to add between them. So this has a certain density, which is hidden in the total mass of here. And then when you do this, then you have to just take independent Brownian bridges going from the points you chose. And this is writing it here. So what I mean by this one, of course, is that if you want to integrate a function, yes, on, let's say, to simplify our lives, on the first part of the path times a function on the second part of the path, I will put, it's B because it's a bridge. What you have to do is, you first integrate over the real numbers, so you put DC, And then you integrate according to this measure. So you integrate expected value of going from x to c of if of f times expected value of x of c to y in times, so here is time t1, here is time t1, t minus t1. Okay. So this is what I am meaning, and these type of functions characterize completely your probability law. One can think a little bit about how it works, but it's third. So this is going to be a useful way of writing stuff. So this is the second useful decomposition, and the third useful result will be just recalling how one computes conditional probabilities. Okay. This third useful. Let's see if it continues being useful. I have to. Oh yeah. Okay. So essentially, we are going to have explicit probability measures, and somehow we will have to compute conditional expectations. And this is like it will be for people who know it, it's just like basic probability 1. But when one doesn't know it, things get complicated. So we are always working. So imagine that we have x and y. They are random variables in a Polish space, and I'm using whatever classical probability things we are, and they are distributed in log. According to, well, for y, you have a mu y. You have a measure nu x, which is mu y, sorry. For each y, you have a measure nu y, that it is a measurable thing that measures just x. You have here f of x, measurable function, whatever. I could have hidden the f here, but somehow it's nicer to write it like this way. And so we will have a lot of measures like this. We have a space x, a random variable x, in a Polish space, a random variable y in a really weird Polish space, and we'll be able to explicitly write its decomposition, and we want to compute the conditional expectation. So the law of x given y is equal to y. This is so when one conditioned, it has a conditional law, and the conditional law is essentially, I will write it in this way, the law of this is proportional to fx y, so y is fixed, mu y dx, meaning that if you want to take conditional expectation of f of x given y, this will be equal to the integral of fx f of x y mu y dx divided by the integral. So this is over the space of possible x's. So I will write x by really abusing notation, x as the place where x takes values. So it's the Polish space, and here I have x. Okay. So I hope this was not surprising, but in a way one can, I mean, if you have never seen something like that, because somehow everyone tends to miss these type of things between probability and probability 2, essentially one just sees that this is something which is y measurable. So the only thing to check if it's the conditional expectation is to just check the definition of the conditional expectation, and it just works out. Yes. Okay, let's now go to really what we do care about. That is the point to study the metric graph. I should have watched this before. So everything we have seen now is just like certain tools that when one realized they are quite elementary, but for us it took quite a lot to realize that these were essentially the things we needed. So now the main idea is to try to answer the questions I have just raised in the context of both, in the context of the metric graph, And so take lambda finite graph. Okay. So we are always going to be working with finite graph. We are never going to get into the infinite story. But what we are going to be interested is define lambda tilde its metric graph. So this is going to be a metric space, a continuous metric space, such that where I'm going to define to explain how you build it. Each lambda, each edge of lambda will be replaced. Is replaced by an interval. And here I have to be a little bit, you have to allow me to put a little bit of things. So it will be a linear length of the edge. Sometimes I'm going to write this. Sometimes all of them are going to be the same and they are going to be t. Sometimes they are not all going to be t. Yeah, I have to somehow define, because when we use the Markov property, we will have to get some generalized things, but I don't want to recall that every edge has a length in my head. But you have to. Yes. Okay, so essentially the main idea is that if you take a graph, so it doesn't have to be planar, but okay, we are drawing here, so we have this graph, and now my metric space is also this part. Yeah. So if it's planar, I can think of it as a subset of a tree, and I think of it as having length. Let's for simplify now, everyone has length t. And the time is going to play a role because it played a role in the Brownian motion, so that's good. Okay, so let me define what our objects are going to be. So what we are interested in is which objects have the Markov property and which are the only ones that have it. So I will start with the answer. I will define. So I still haven't stated what the Markov property is, but I will start telling you what the object we are interested in. So define. So this is the definition of generalized Gaussian free field. Some other people call this generalized Ising model. Not exactly the definition that I'm going to put, but all. So generalized Gaussian free field. So we say that a continuous function phi tilde, so I'm trying to put tilde everywhere where I'm talking about the metric graph. If I don't put the tilde, that means that I'm just looking at the restrictions on the vertices. Somehow simplifies life. So that goes from the metric graph in this context to R. If one thinks a little bit about it, of course I can do it in a more general space, but it will be just more confusing. So we set a continuous function that is a generalized Gaussian free field if there exist measures mu v in lambda. So I have a set of measures, okay, such that the probability of, let's say that d phi tilde belongs to d phi tilde. So I'm a little bit, so this is proportional, so there will be a product. So on the vertices, on each vertex, I will have base measure mu v. So here I have mu v of the value psi of v times, and here, so this is for every vertex, v in lambda, and for every edge. So here I will abuse notations. I'm not orienting edges, but I will choose an orientation just to count them once. For every edge, so I will write ij we will do the anomalized probability measure, the anomalized measure of length t, or you can change it by the length of the edge, okay, of d psi tilde restricted to the interval ij. Okay. So this looks daunting. I mean, this is complicated because it's a probability measure on a space of continuous functions on lambda tilde. So I have to pay something. The good thing of writing it this way is that afterwards we will get quite easy ways of decomposing and getting probability measures. So maybe let us do some computations to see that we are getting what I'm writing here. So the first thing one is interested in is what is the marginal law on the vertices. Yeah? So this is a complicated law, but I could try to see what the marginal law on the vertices is, and we will see that this is something we know quite well. Okay. So the max. What is the law of phi? So when I write phi is because it's just a projection on the vertices. Phi tilde is everything in the phi. Well, this law has to be proportional to integrating there everything that lives on the edges. So it will be so here we get a product of mu b, phi b, psi b, and here I get a product on I neighboring j of p tilde of psi I, psi j, and t. But we have to integrate this over values on the edges. So this is an integral that has as many integrals as values on as edges there are, and they are integrating over continuous possible functions. So that we can change this product with the integral, and we can see that essentially we just get the total mass. So this one doesn't touch here, and this is equal to total mass, and the total mass, sorry, speed check, the total mass of this was pt going from x to y of the product of mu b psi and p psi t. And this pt, in our case, we were always thinking about this as the Brownian motion story. So we come back to something more concrete. So this pt is exponential, sorry, it's product. I did whatever I wanted. It's product of the edges of psi I going to psi j. Okay. So this, in our context, is just exponential of minus 1 over 2t psi I minus psi j squared. So I was writing something really complicated to say this. Okay? So our marginal law is just the energy of what? Well, it depends. So, example, if mu b is equal to a Dirac minus 1 plus a Dirac 1, well, this can just take two values. And the energy is this is an Ising model. At temperature T or beta equal 1 over. Okay. So it was simple. I was not hiding something. So what happens if mu b now is Lebesgue, and for all b different than b0, and mu of B0 is just a Dirac non-zero. So this is just a GFF in lambda with boundary condition with the GFF in B0 equal to 0. So we have to pin down the GFF, if not, the thing is not well defined. And of course, this is all hidden in the fact that in my definition, I didn't write a partition function, so I have to integrate around all of these things. And either the partition function is finite or it's infinite. If it's infinite, this is, of course, it cannot be defined. Or it can be finite, in which case can be defined. And as we can see, we saw just the measures on top of, the vertices. And now we realize, and this is the one just giving us the partition function, because the partition function, we just have to integrate this again. So we just need to see that the partition function on the vertices is working. And the second remark, conditionally on phi, so conditionally on the values on the vertices, what are we doing on the edges? Well, conditionally on the value on the vertices, now we can use our conditional probability thing. So now we have a conditional probability on the edges. So we have that the probability psi tilde of phi tilde in psi tilde given phi equal to psi. So given that I know what on the vertices is, this will be proportional, and my result tells me just forget about the measures on B. So it will be proportional to the product of the edges of this P y. So this is psi I, psi j, length t of d psi tilde restricted to the edge I. Okay, but this P tilde, I'm having a proportional, but this psi I and psi j are fixed. Yes, I am conditioning on this. So I can forget the check. I can forget it because the total mass is just a constant for everyone here. But this is just telling me that in each edge, this psi tilde restricted to the edge is a Brownian bridge of length going from psi I to psi j with length t, and they are all independent because they are a product. So this is independent Brownian bridge. This is why this conditional thing, even though it looks simple when one is trying to do computations, it simplifies quite a lot. So essentially what I have done is the following. So I wrote something really complicated, but it can be summarized as follows. Just take a generalized Ising or generalized Gaussian free field on the vertices. Meaning that you choose different measures for each vertex. So for one vertex can be, let's say, -1, 1. For the other vertex can be the integers. For the other vertex can be Lebesgue. For other can be whatever. Fix in each one a measure, and then just take exponential of an energy. What is the energy in this case? It is because it's a product, so it is the Dirichlet energy. No, the product will transform into a sum. You take a Dirichlet energy, and then afterwards, just write a Brownian bridge connecting them of length t.
So is t again the length of the segment?
It's the length of the segment, yes. So one can think that I didn't want to write the length of the segment all the time, even though I should have, because then I'm going to need it.
But it can be different for each.
It can be different from each edge, yes. I mean, nothing I'm doing, up to this point I'm defining this, and now I want to define, okay, so I wrote this in a really complicated way, and the reason is I want to prove a Markov property. So I will have to condition. And so on top, really complicated, I hope that remark 1 and remark 2 make things more easy to digest. It's just like you take this field, and then you add just independent Brownian bridges in each one of them. And this can be written in that really nasty way on top. So now, we want to show that this object has a Markov property. That's what the title was. And now we have to think what Markov property means. And I claim that there are several definitions for the Markov property. At least 2 in this context. somewhat. So, one can give me one definition of a Markov property on the metric graph. So let's do it simpler. What do we understand as Markov property in A? Like if you have a Markov process, what is the Markov property? Help me. I don't want to be alone. Yes, you can speak.
Being able to write inside of a smaller area, you can write what is there as being dependent on the outside, condition on the boundary.
So this is one definition of a Markov. Let's talk dimension 1. So it tells you that conditionally on the present, the past and the future are independent. Do you agree that that's a reasonable definition of a Markov property? Or not? So is that, okay, does anyone know another Markov property on time? Is there another one? Or is that the only one? I claim that there is another one.
It's just the same process stuff.
Yes, it is the Brownian motion one. No? So if I tell you the Brownian motion has a Markov property, you are not only saying that conditionally on the present, the past and the future are independent. When it's saying like, given at time t, what I have forward is just a Brownian motion on time. Yes, so this is stronger than the classical Markov property, and we talk about them like they were the same, but they are not. So one has to have these two objects are living in our heads.
Is the second one stationary Markov property?
It's like stationary, but it's somehow like it depends on how much information you are getting. So for the Brownian motion, it's not even stationary; it's like even more. For the other one, it's like you can describe your process on time by one. So there is the homogeneous time, which tells you that you just need to care about the point you are. There is the inhomogeneous, where you just need to care about x and t. And like the weakest form of the Markov property is just telling you independence given the boundaries. So I do not know if in R, having the Markov property implies that you are directly inhomogeneous. Yeah, it should be. But it's just like having independence from the present, from the future and past given the present. So we have to do equivalently this in lambda tilde. And as Leandro proposed, essentially instead of looking at times, now we are going to look at boundaries, like boundaries that separate my space. So I have a set k, and the set k has a boundary, and what we want to say as a Markov property is that the inside and the outside are independent. So Markov property 1. So let k be a closed set. We said that phi tilde has the Markov property so the first definition, if conditionally on the values at the boundary of k, the values on top of k are independent to the values outside of k. Let me do a drawing. An object here. So this is our domain. And we have maybe. Okay, so that was my graph. I shouldn't have used the event. And now my set k is this thing. It doesn't have to be connected. And it doesn't have to just get one connected component. Let's separate these two. Okay. So if I know the values at these lines, which have the boundary, then the values inside and outside are going to be independent. That's just my basic Markov property. We have a second type of Markov property, which will be stronger and which is like the version for the Brownian motion, which will describe this law. So the same, if phi tilde has the Markov property, for this one I have to take phi tilde. Okay, no, has the Markov property. It conditionally on phi restricted to k, phi restricted to the complement to the just purple parts has the law of a generalized GFF on lambda tilde minus k. So what I want to say, so if k is empty, then that immediately implies that this phi tilde has to be a generalized Gaussian free field. A generalized Gaussian free field comes with a choice of measures mu v and a choice of length. Okay, so assume that those are fixed. They are already deterministic, both the length and the measures I'm taking. Okay, now if I condition furthermore, so if I furthermore condition on the values on k, the law outside will be just a generalized Gaussian free field with the same measures, but now I have boundary conditions here. And now note that the lengths have changed. So here is the same value, okay? But I have to add this energy. Wait, maybe. So now the length changed here. You agree with me? It changes according to how big it was. And I have to add the interaction from this point to this point, because these ones are fixed. If you want it in another way, I could have put vertices here, and I put Dirac's that are exactly the boundary values, and that's the law. So, one exercise is to show that 2 implies 1. So if you can describe the law given k on lambda k with boundary values phi tilde restricted, because you can describe the law and it only depends on this value, then you get independence. So we have these two types of Markov properties, and Markov property 2 implies Markov property 1. So let's show that our Markov, that the generalized Gaussian free field satisfies this Markov property. So proof. So proposition. A generalized GFF satisfies the Markov property 2. So this is why we wanted this conditional thing. We have to write the conditional expectation. So what is the probability? So I will get phi restricted to k. So I call this deep side, and phi restricted to k prime. So to lambda tilde minus k will be this side. So essentially, the proof will boil down to just writing down correctly our probability law in such a way that we can describe our conditional probabilities. So okay, so now we are going to say, so this will be proportional, and we are going to separate edges into 3. Edges that are completely containing k, edges that are completely containing lambda minus k, and edges that are between both. And for simplification, because if not the proof it will be longer than what it is, I will assume that there is only one cut here. Of course there could be many cuts in one edge, and one has to further separate them. But we will assume that each edge has just one cut. So first, the product over ij, where both are in k. So here we will get p, so this will not change, of psi I, psi j, product over the vertices in k of mu v of d psi e. Now, let's put on the bottom all the edges that are completely contained in lambda tilde minus k. So I neighboring j, I comma j in lambda minus k. So these are vertices, so these are edges, so p, so I will get gamma I, gamma j, product of b in lambda minus k, of mu b of b psi d gamma b. Okay, so now the interesting thing is what's happening exactly on the edges. So on the edges where there is 1 point breaking it. So this will be the product of I neighboring j such that a belongs to k and j belongs to the complement lambda minus k. And I will get exactly the same here. Pt hash of psi I gamma j. So I'm going from a one value that is given by this object to one value that's given for that. Okay? And I want to rewrite this. So we are going to rewrite it using this thing. So we have to break it down in the midpoint. So let's assume that that T1 is the S is the endpoint point. So this point we call it S of ij. Okay? Or just S. Well, I will call it S of ij. Okay? So then if we can break this anomalized probability measure will be equal to, maybe I just want to put this part so I don't have to write the plot again. P of going from psi I to psi Sij in time Sij times P of going from psi Sij, or I could put gamma of Sij, they are the same, to gamma of Sj, of j, in time t minus Sij. And I have here, I have to add a Lebesgue measure living on top of the gamma. Deep gamma. Or the deep side. Okay. Yes? So this is just breaking this probability apart into the first part times the second part. In which, so I'm hiding here that I am, because I'm hiding here what is the length, so here I am measuring from time in the restriction of psi tilde to the interval ij. Here it's the interval, the restriction to the interval psi I is ij, and here you have the other interval. Okay? So I'm hiding things under the carpet, but after one has written it down, like this, one can see terms. So essentially, all of these terms depend on psi tilde. So if I want to condition on psi tilde, I can just forget them. Okay? Maybe this is what I want. So I want to condition, so I have a measure living on top of that is just caring about psi tilde. So this implies that the probability of phi given lambda tilde minus k gamma tilde given phi restricted to k in psi tilde. So this is proportional, and I have forgotten everything of this, and I will get the product of P minus Sij, psi tilde would be of Sij going to gamma j times the probability, the product of the other ones. So I don't want to write the ones below because it will be a little bit of a mess. Gamma I, gamma j times t times the product over b. I shouldn't have written. Okay, b in lambda tilde minus k of mu b d gamma. Okay, so this looks a little bit complicated, but it is a really short way. So what I wanted to give with this message is that there is a computation after one has written things down properly, and one is used to manipulating conditional expectations in this context I told you. There is a somehow direct proof that gives us that the conditional probability of this given that one, it can be written as this. So this feels exactly like a generalized Gaussian free field, but there is this term, and this term is just that I am adding a vertex here, and I am fixing this length to be whatever it has to be, and I am fixing the value there. So it's exactly the law that I described. So it is a really complicated way of seeing the law that I described. Maybe. So I have to give 15 minutes. I think this is a good time because we have seen something, and after the break we are going to see why these are the only ones that satisfy this property.